been working in NRM sector, including resource conservation and livelihood, for 29 years in Maharashtra and worked in Himachal Pradesh, MP, and few other states. Worked for 14 years in NGO sector. Later joined Yashoda, that is SIRD Maharashtra, as research officer. Worked as DPME IFAD supported project and further appointed as senior advisor to Principal Secretary Water Conservation, Government of Maharashtra. He is having an experience in project management ranging from planning to monitoring and evaluation, largest being Integrated Watershed Management Program, which is now called as PMKSY Watershed. Water sector field and policy initiatives for water security, groundwater recharge, water literacy, water quality, water budgeting, cleanliness campaign, well recharging, etc. has been its area of specialization. Evolved monitoring, evaluation, and learning documentation is MELD for IWMP projects. He is a team member for studies on climate change and agriculture of water in Maharashtra. He has developed proposals on climate adaptations, watershed plus drought resilience in Marathwada, as well as protecting upper catchments of Bhima River Basin. Along with NRM, his work for community empowerment, decentralized planning, integration of social sectors and rural livelihoods in Government of India, NABARD, UNICEF, World Bank, ICF, Aga Khan Foundation, and DIFD supported projects. Represented in state and national level committees for institutionalizing and strengthening watershed projects since 1994. Contributed for policy studies of watershed and rural livelihood. He has conducted appraisals, budget planning, reviewing, monitoring, and evaluation of DPAP, IWDP, Hariali, NHWDP, IWMP, and such other projects. He has worked on and developed many innovative concepts in NRM, community monitoring, groundwater management, artificial aquifer recharge, etc. And he has published many more articles on the same subject. He has facilitated convergence at various levels within government departments and agencies, of scheme at project level, and of approaches at district level. He has been delivering lectures, talk sessions in classrooms as well as online training workshops. And in the same series, he is going to speak with us today on water ecosystem challenges and water stressed districts in India. Jayant sir, over to you. Thank you.
So we will be discussing about this water ecosystem challenges in India. It is like a brief journey going through some global scenarios and some even district level scenarios where it helps us to understand something about water. As we all know, water is a very vast subject and surely it cannot be dealt in one lecture. But we'll try to touch on the more important points, our interest. I would like to also clarify that here, when we say water, it is water related to the usable water for human mankind. And the ecosystem does not truly mean the whole ecosystem like in environment science. It is an ecosystem components related to the usable water and only few which are in the preview of the present. So I like to call this presentation or this discussion as something like watery bumps or bumpy whatever you would like, because you would feel so while going through this presentation. There are some unique characteristics of water which makes water very peculiar. These are the characteristics like polar nature, then cohesion, where water sticks itself, causing surface tension. Adhesion, water sticks to other surfaces. Capillary action, water rises against gravity, like from roots to leaves. There's anomalous density water, where because of which we see that ice floats on water. And water is a universal solvent because of the ions and hydrophilic solutes easily dissolved in water because of its polar solvent nature. We'll have a global overview of the water resources. We all know this water cycle. Maybe you will be feeling that these are very basic things being presented, but as I came to know that there are some learned scholars, eminent personalities, as well as there are some enthusiasts and some even students. So this is something which will touch upon all those aspects related to water. So this is a water cycle which we have studied even at the school level, and we know that from water evaporates from the ocean, it condenses to form clouds, and then it precipitates in the form of rainfall, in the form of snowfall. It accumulates in the mountain peaks, it flows through the rivers, it accumulates into the lakes, it then forms soil moisture, flows back to the ocean, and keeps on cycling. So as we saw in that quiz, 97% of the total Earth's water is in oceans. Which means that there are only 3% of water is termed as fresh water. Out of this 3%, 70% is in ice caps and glaciers, 29% is in groundwater form, and only 1% water is easily accessible fresh water. This 1% is of the total 3%. And of these 1%, then again, 52% is in lakes, 38% is soil moisture, 8% is water vapor, and 1% in the rivers and all the living beings. So this gives standing of how scarce the usable water content is, considering the whole water system. We know because of the water on the earth, it's called a blue planet, or it's seen as blue. But this blue nature, out of this blue component of the planet, it's hardly a small fraction which is utilizable and can be used for the mankind or the living beings. So that's how the importance of water can be described. Now that was in abstract terms. Now let's see how it is in absolute terms. So total water in million cubic meter. Those who can have that calculations, please they may work it out to go into liters. But then million cubic meters is a vast volume and difficult even to imagine in the form of liters. So you can have simple mathematics where we can work out even with liters. But just to understand the volume, please try to understand and keep the unit as million cubic kilometers. So total volume of water in 1,386, of which salt water is 1,344, fresh water is 35 million cubic meter, and water vapor is 7 million cubic meter. And of this 35, then as I told you, 25 million million cubic meter is ice caps, groundwater is 8, and surface water is 2 million cubic meter. And the surface water distribution again is 0.82, soil moisture is 0.43, plants animals is 0.40 million cubic meter, and rivers and streams is 0.05. So only 0.2% is usable water, and we are discussing about this usable water in the perspective of this session. So the dams are constructed on rivers, so the water flowing through rivers is accumulated into the dams. Can be various kinds of water storage structures. So now coming to, so the total average annual rainfall is 1,170 mm. This is something, a long period average, which the IMD terms it. And when this total precipitation, when this rainfall is converted into a volume of precipitation, comes to something 4,000 billion cubic meters. So 1 billion cubic meter is 1 cubic kilometer. And the total availability out of it is 1,869 billion cubic meter. You can always convert it into percentages also to have a better understanding of it. Like 1,869 is something 48% of the 4,000 billion cubic meters. And of this, the utilizable part is 1,083. Let's say 1,000 billion cubic meter, 25% of the 4,000 billion cubic meter of the total volume of precipitation. Now, even within this 1,000 billion cubic meters in our country, which is utilizable water, usable water, surface water is 690 billion cubic meter, groundwater is 393. So even then, again the percentage, when we draw down or go into more granularities, we make it more precise to understand of what kind of nature, what kind of source, what kind of resource the water we are using. The demand against the availability, then we also have to think about the demand. So irrigation demand is 543 billion cubic meters. As we say that India is an agrarian country, 85% of the water requirement is for irrigation and agriculture. But friends, it's also true to some extent even at the global level. The freshwater consumption for agriculture in the world is roughly around 65%. So it's just not India where it is more dependent use for fresh water. It's also the global scenario with some variation. But 65% is also very, very high. Domestic water requirement is 42 billion cubic meters, 37 power and all this. So these are the different distributions which we have. Then this is one more information, as we saw in the earlier slide, that the total availability is 1,009 billion cubic meters, of which utilizable is something around 1,000 cubic meters. So this is the distribution of that utilizable surface water, which is in different river basins. So Ganga has the largest contribution, 36% of this total utilizable water. Then second is Brahmaputra, but you can see a very important concern over here, that Ganga has a total 525 million cubic meter of water resource. Brahmaputra and Barak has 585. But out of 585 Brahmaputra, only 24 million cubic meter is utilizable for India. So So we have to also think that it is always not the whole water resource which is available to us which can be utilized. Then therefore what happens, like, then though Brahmaputra is a very large river having lot of water in volumetric terms in its basin, Godavari stands a second with 11% contribution, and then third is Mahanadi, and followed by Krishna followed by Mahanadi and other rivers. So this is the distribution. Now it is also important that when we say that 1000 billion cubic meter is utilizable water available in India, the spatial distribution of this water is not uniform. So obviously the utilizable potential in different regions or different river basins is different, and obviously the conservation practices or utilization patterns have to be in line with with the availability. Then as we saw in this earlier slide that this surface water is 690 billion cubic meters and groundwater is 393 billion cubic meters. So something around 40% comes from the groundwater, which is of which 91% is usable recharge resource, and if we see the recharge pattern, we will see that the monsoon rainfall, which is in global terms termed as summer rainfall, recharges nearly 58% of the groundwater out of this 91%. And then non-monsoon and other sources also help. Even to as you said, that dams and rivers and lakes, these surface water bodies also help to recharge groundwater, and that percent something goes up to something 18%. So those conservation structures also help to recharge and retain the groundwater level. So that there are different uses of water, and that's why it is very, very important. It's just not life support, it's also socio-economics of the area, which are governed a lot by water. So water has upstream uses where water is pumped up or drawn out or diverted or something like that for agriculture, thermoelectric, industrial, mining, drinking, domestic and commercial purposes. There are in-stream uses like hydropower, navigation, recreation or ecosystem support system. And these also depend on the local geography as well as the socio-economic patterns in that area. And that's why water then becomes a very, very important issue, just not to support the life, but also to support the socio-economics of the area. We know water is life, but it's a concern for life. Then I have tagged it with 2 question marks and 3 exclamations. So is it really a concern? That also we have to think. And why it seems to be a concern, that also we have to think. So let's move into that those aspects where we will have to think about some determinants, whether it's a concern, and if it's a concern, to what extent and how. There is the per capita availability in India and the various demands. As we know that it is going on increasing. If we think about the stress line, which is 1700. And the scarcity line which is of 1000 cubic meter per capita, we fear to be nearing that scarcity line by 2050, which is a concern for us. I'm not saying saying that this is only because of population and some such policies or something like that, but then that's a fact. This is happening and we have to address it. So let's think about it. Be prepared. Let's take some measures to address the situation. Then only we will be able to move along. Central Government Board has conducted a lot of quality studies also, and as well as the quantity studies. They have defined like that it is safe to withdraw less than 70% of the total annual recharge in an area, right? So if we are receiving say 1000 liters of water through natural recharge, it is safe if we use 700 liters and have a carryover concept of 300 liters for forthcoming years. But there are areas where this is withdrawn more. There are even areas where it is withdrawn more than 100%. So if, we receive 1000 liters of recharge in a year, and we are using more than 1000 liters which is leading to exploitation. As we always read, that we are using water which has been stored from thousands of years, and now we will be depleting from that precious resource and all those things. So we have to think about it. And friends, see that this withdrawal of the type of semi-critical, critical, or overexploited is in 36% units of the total units in the country, and of these 36%, nearly 2/3 fall in Punjab, Haryana, Rajasthan, UP, Tamil Nadu, and Telangana. So now the stress in terms of availability of groundwater, where the socio-economic dependent on groundwater also changes along with the usage pattern. So probably these areas will have to think in a different way so that they are able to overcome these issues and bounce back to normal situations. So this is something quality issues which. Then this is one more determinant: water pollution. We know all these causes, agriculture, industries, mining, and we are very close to it. We surely know it. But this is one determinant which reduces the utilizable potential of fresh water. Then climate change is one more determinant which surely affects precipitation and the temperature. We see the changing pattern, means the anticipated change in precipitation, which shows that the precipitation will increase along the equator, will increase in the polar areas, but it will reduce in the inhabited areas of the world. So the major concerns are spatial and temporal variation of rainfall, reducing per capita availability, increasing the water stress, food requirements of the increasing population, 30% increase, overexploitation of the groundwater, quality issues of surface as well as groundwater, narrow perspective of the conservation concept, and climate change implications. So these are the major concerns which we will have to deal. There are ways of dealing it. But what is important is we will have to think beyond and act beyond. Just by putting up articles and putting views will surely not help. It will surely flag the issues, but then we will have to think beyond this scenario and also have to act beyond this scenario. Then only it will be possible for us. So there are a lot of options, and these are some calculations like I don't know, means this is actually very simple, but maybe within a minute or so I'll try to explain it. Say at an average area of average village area in India is something 500 hectares. Say a less rainfall area, we are thinking it is 500 millimeters of rainfall. It will yield something 250 hectometers of water or 250 crore liters. Say the population of this village is 1000 and it has a similar cattle population of 1000 which requires nearly 5.5 crore liters of water, which is only 2% of the total rainwater. So if we calculate the total rainwater in this area, which is 250 crore liters, the total population requirement of that area along with the cattle is only 5.5 crore liters, which is 2%. And if we say that we are not able to manage even 1.5 or 2% of the demand, then probably it's only poor management, nothing beyond that. If we think about the Pune metropolitan area, which is 570 square kilometer, which receives 700 millimeter of rainfall, which has 40,000 crore liters of water, and for a population of 60 lakh, even with a supply of 135 liters per day, it would require only 30,000 cubic meters of water. So if we are able to conserve, say 60%, 70% of the total rainfall we receive on the Pune metropolitan area, it will suffice the large need of this municipal area. And then water from Panche, Khadakwasla, Mira Bhatgar, all these can be used for productive purposes. So that's why we need to have a different perspective while dealing with this issue. This is for the hydrology for the rural areas where we have heard about watershed development. Many eminent workers have done a lot of work in watershed development, and it has proven it's a proven conservation practice. See, like simple the CCT which we see on the hills and mountain slopes and all those things. So 15 to 20 hectares of CCT done in a village can fulfill the total drinking water requirement of 1,000 population. Only 50 to 20 hectares of area. 20 hectares is how much? 20, 40, and 48 acres of land. If 48 acres of land is done with this kind of conservation practice, it can fulfill, means equal to the drinking water requirement of that population. So that can be one good measure. There are many other benefits of having this kind of soil water conservation measures. Then the organization which I have worked with, that Bharatiya Jain Sangatna BJS, it has an approach of rejuvenation of water bodies, which is decentralized mode and more like a people participation mode for conservation practice. Then for the urban areas, there has to be some different approach. This is RRR approach, where we can have an integrated way of doing it. If we think about a small plot of with a small building of 50 square meter to 500 square feet kind of thing, and it has 10 mm rainfall for at least 20 times, that 200 millimeter rainfall, if we are able to harvest, then we are able to harvest nearly 10,000 liters of drinking water and storm water, roof water and storm water in the small plot of 1,000 square feet. Then there's also a very important thing which we need to consider about artificial recharge. Because as we discussed, it's a heterogeneous geology, and there are limitations of natural recharge. So we can think of having additional recharge, and if we are able to do it as a study estimated by Aquatam, that 140 million cubic meters can be recharged annually in Pune metropolitan area, which is something about 45% of the total supply or requirement of the Pune metropolitan region. So these are the some approaches which we can surely think of. The inclusive approach for water conservation is the first and foremost is it is not a task of one or not a task done once. It is part of the ecosystem, and so water has to serve the ecosystem. It cannot be like okay, this year there's very less rainfall, so we will not use water. We will try to have supply only for drinking purpose, only for say some very limited purposes, and we will not have cropping or crops, or we will not use it for some other ecosystem services. So it's not possible thinking in that way. Water is a resource; it's must for life, and water is a dynamic resource. So it is very dynamic. You cannot simply store water. Like if you store water into dams and lakes, and it evaporates. If you don't use it, it is not that it will remain for the next rainy season. It will evaporate to a lot. But the good opportunity is that India has a historical wisdom of water management, and the driver, water is the driver for the Indian economy. So we have to also think in that perspective. There are different approaches: harvesting, scaling, recycling, quality, quantity, productivity at the core. Then we have to think about water literacy, river basin, sub-basin planning. Because district cannot be, district as an administrative unit is not a natural unit. Like if we think about, say, like Pune, where Lonavala has lot of rains, and Daund Baramati has something only 400 millimeter of rainfall. Say the same cases in Satara, Mahabaleshwar has 4,000 millimeter of rainfall. 40 kilometers down the slope in Khatav and Man, it is 450 millimeter rainfall. So, and both these regions fall in one district, like Lonavala and Baramati Daund are in one district. Mahabaleshwar and Khatav Man are also in one district. So district as a unit is difficult to actually think about it, but it is only an administrative unit for the implementation. But the planning should necessarily be a river or sub-basin kind of thing approach. And we also have to think, when it is a socio-economic determinant, we also have to think of demand management as well as virtual trade water, which is bound to come through, because for areas which are water scarce, they still require an equal amount of food. It cannot be said that we receive only 400 millimeters rainfall, so we will be eating only millets. We will not go in for pulses or some other kind of food items. So it is the consumption requirement of a human body, and it has to go. So we'll have to think about virtual trade also. So I would like to acknowledge all the references which I have done for this presentation. I thank you for your patient hearing through this session. This is something which I has spoken about a long time earlier by Rahim. Rahiman pani rakhiye, pin pani sab sun. Pani gaye na ubre, moti manush cho.
Is there any estimates for recharging and what is the cost of recharging per 1000 km? Something like that.
As I said, there are different conservation measures depending on the local situation. Like if we think of recharging, this is a very systematic way which has been designed by an institution named as Aquadam, which is also Pune based, and they have done a detailed study for the geohydrology of Pune. See that it's very peculiar. If you can see through this slide, this is a filter. Okay. This is a shaft for a bore well, and this bore well should be extended to a depth where we have water table as well as some porous formation, so that the water fed through this recharge shaft can reach out and recharge the layers beneath it. Okay. So if this, and the second is, depending on what type of inflow it is having, the filter system also has to be designed differently. So if we are able to keep our roof clean, just I'm putting an example, clean, we are trying to maintain it, flush off some of the dirt during the regular monsoon showers, and we have a simple filter system with maybe a bore well to a depth of say 100 feet, which yields good groundwater for that area, then probably this would be a broad estimate of 5,000 to 7,000 rupees per unit. Okay. But if this also has a storm water, like the water flowing from the boundary areas of a society, maybe a multi-soil society, and vehicles moving in over there, probably then this filter system has to be different. It also has to take care of the oil spills and the dirt and all those things. And then this filter system would be costly. Maybe it would, and it also depends on how much inflow it is receiving. So if more the inflow, then the filter system size will be more. And if it's a small limited surface area, then what generally is observed or calculated is, for an area of say 500 square feet of rooftop, 5,000 to 7,000, 7,500 is the expenditure for this filter system. And bore is already existing, so we can have some fixtures for this bore so that it operates in a proper.
See, another thing is that I attended some interactive sessions from the Institution of Engineers. Since I'm from the Andhra Pradesh side, okay. We have a very long coastal line. So there was a paper or a scientific study from Institution of Engineers that we can use the entire industrial water consumption, we can feed through desalinated water, so that the extraction of water or utilization of groundwater will come down, and the treated effluent water after particular processing can be discharged into the bore wells. So this is the reverse type of thing. Instead of taking out water, we pump in water into the earth, but take out water from the seawater desalination, and the per KL was costing around 70 rupees. That kind of calculation was done, and that same is applicable for Maharashtra also. Have you done any work on this side?
Regarding coastal area treatment or saline ingression or treating seawater for municipal supplies, there's hardly any work done in Maharashtra.
Okay.
Yeah. Most of the work we see over is in only Middle East, where it is claimed that 70% of the municipal supplies are through desalination of seawater. The second part which the earlier part which you said, that using treated effluent to feed in the aquifers and raising the groundwater levels, yeah, that can be done. It would be a costlier affair. But anyways, if the effluent is treated properly to a level that it can be fed into groundwater, it can surely also be fed into streams, and that would better maintain the ecosystem in a better way instead of feeding in directly to the groundwater.
Yeah, you are right, sir.
I feel that being able to build a perspective to think a little beyond on what is generally said in as a populistic statement. So I have tried to go a little bit beyond with some technical information.